force that nothing and nobody can escape. This mysterious force envelops and permeates us, and not only dictates our life on Earth, but holds the universe together. Gravity is the key to understanding the universe.
Gravitation.
Gravity. Everyone seems to have an intuitive grasp of what it is. You have two objects, they attract one another, and that's gravity. But when you delve deeper, it's actually a rather complicated matter. Take weightlessness in space on the space station. A marvelous state. You float in your sleeping bag, food flies into your mouth. When you close your eyes, you instantly get the feeling there's no up or down anymore, because there's no force acting on your equilibrium organ. Does this mean that the Earth's gravity isn't there anymore? Of course it is. But there must be some sort of opposing force canceling it out. But I'll tell you more about that later. Interestingly, weightlessness can be experienced on Earth too, namely on parabolic flights.
A parabolic flight on a converted passenger jet. The airplane flies a so-called ballistic trajectory, a parabola. From level flight, the aircraft is put into a steep climb. During the ascent, the engines are throttled back. During the subsequent gliding phase, the passengers experience zero G for around 20 seconds. Weightlessness.
You first have to understand what weightlessness is. A common misconception is that weightlessness is synonymous with the absence of gravity. This is not the case. You're weightless when you're in a state of free fall. Every time I jump down from something, I'm in free fall. For a brief moment, I'm weightless.
That's the principle behind parabolic flight. The airplane and passengers on board are both in free fall, like a thrown rock. The pilots initiate the parabolic trajectory at an altitude of approximately 6,000 meters. Then they throttle back the engines. The plane continues to climb without accelerating, and from this moment up until they pull out, the jet is in a weightless condition for around 20 seconds. The flights are made in order to perform scientific experiments and also to prepare astronauts for their missions. And every now and then, guests are invited along to the zero-G adventure too. Such missions are flown by experienced test pilots. During the climb and until the engines are throttled back, the passengers experience twice the acceleration due to gravity, 2G. Once thrust is removed, the weightless phase begins, 0G. The plane climbs until the Earth's gravity gains the upper hand and causes it to fall toward the ground. The pilots then initiate the pull-out maneuver. After a free fall of about 2,500 meters, they then level out again. During this maneuver, they once again experience twice the Earth's gravity, 2G. The plane flies several such maneuvers in succession during a mission. During the parabolic phase, there are 20 seconds of microgravity available for performing experiments. Any longer than that, and the airplane would get dangerously close to the ground.
The weightlessness we can experience on Earth usually comes to a fairly abrupt halt, due to the fact that we hit the Earth again, which is the negative part. But in principle, we can experience weightlessness in any form on Earth. If we want to experience it for longer, though, we have to go to the International Space Station.
May 2020, a Falcon 9 lifts off for the International Space Station. It's the first manned flight conducted by the private U.S. aerospace company SpaceX. The spacecraft is bringing the two U.S. astronauts Robert Behnken and Douglas Hurley to the ISS. The International Space Station has been in operation since 1998, a highly complex research laboratory in weightless conditions that's permanently orbiting the Earth. Or more accurately, that's falling around the Earth.
Schwerelosigkeit bedeutet, ich befinde mich im Freien.
Weightlessness means being in a state of free fall. I could naturally ask the question, why are they in a state of free fall in the space station? They're falling towards the Earth the entire time, but their horizontal speed is such that they continually fall past the Earth, which is why they're in free fall the entire time and thus weightless.
The International Space Station is the only place where scientists can conduct research on a long-term basis outside the influence of gravity.
Quarter-turn buckle test. 604 pounds of support test.
Humans are adapted to the Earth's gravity. And so the space station is also used to investigate the effects of microgravity on the human body. Researchers want to explore the solar system and travel to faraway destinations. Mars, in particular, has captured the imagination of scientists. But on the journey to Mars and back, explorers will be subject to zero-gravity conditions for many months. A manned mission to our neighboring planet would take 2 or 3 years in total. An unusual NASA study reveals what the consequences of such long-term missions could be for humans. The astronauts Scott and Mark Kelly are identical twins. One of them spent a year in the Earth's orbit. The comparison shows that weightlessness over a prolonged period of time causes muscles and bones to atrophy and impairs the cardiovascular system. It also affects the immune system and the eyes. In addition, long-term stays in space result in changes and damage to the brain and the genetic material of the astronauts, including to radiation exposure. In this way, the space station orbiting the Earth shows us how important the Earth's gravity is for the human body.
So what does an apple have to do with gravity? As every child knows, this is where Newton comes into play. But let's start with the basics. Here's the Earth, here's the space station. It feels the pull of the Earth's gravity, but doesn't fall to the Earth. Why is that? Well, there must be some opposing force that cancels out this attraction. And this is the so-called force of inertia. Every object, including an apple, that is accelerated builds up inertia, and we call this the force of inertia. And when I make it orbit, this inertial force points outward, and we call this centrifugal force. So now we can understand the space station. It orbits the Earth and feels its gravity. And because it's circling around the Earth, the centrifugal force balances out the gravitational attraction. So what did Newton see as he was sitting under the tree? There was an apple up here. It fell, and he noticed that it got faster and said, aha, acceleration, opposing force. Inertial force balances out the force of gravity. He jotted it down, and that was his famous law of gravitation. But the question remains, what exactly is gravity? And it's a question Newton was very successful in answering.
A falling apple is said to have led Isaac Newton to his laws of gravitation. Newton suspected that there was an innate force of attraction between the apple and the Earth. He also suspected that this same force governs the motion of the large objects in space. The celestial bodies interact with one another through some mysterious action at a distance. The greater the object's mass, the greater its pull. The birth of a revolutionary idea. The mathematician and astronomer Johannes Kepler had already described the orbits of the planets around the Sun in the early 17th century. The force that kept these planets in their orbits was then described in 1686 by Newton's law of gravity. It also allowed the elliptical orbits described by Kepler to be derived.
You have to admit it's one of the most brilliant ideas ever, that the force that causes an apple to fall to Earth is the same force that keeps the moon in orbit. I mean, you'd have to be pretty drunk to come up with such an idea. That the moon is falling towards the Earth the whole time, but always falls past it. It's falling the whole time, but whenever it tries to fall, the Earth has moved on. So it falls around the Earth and becomes a satellite. That was Newton's idea. He even sketched a picture of it. You can find this exact drawing in Newton's original book.
But where exactly does the Earth's gravity come from? A significant part is due to the Earth's inner core. The deeper down into the Earth you go, the greater the temperature and pressure become. At the center of the Earth, the pressure is then so high that the core is solid, despite having a temperature of over 5,000 degrees Celsius. This is where the mass is most concentrated. The relatively compact inner core constitutes a third of the Earth's approximately 6 sextillion tons mass.
The Earth's core is composed of nickel and iron. They're very dense, much denser than the rock on the surface, which is why the Earth's core plays a dominant role in the Earth's gravity.
The main thing is that the Earth has sufficient mass to hold on to an atmosphere. It's our planet's gravity that keeps the thin atmosphere bound to the Earth, essential for the emergence, evolution, and survival of life as we know it. The gravitational pull of the Earth forces the scientists into space if they want to experiment under weightless conditions. But this is also possible on Earth, using a trick.
You can simulate weightlessness simply by letting objects fall. You just have to increase the free fall time. And how do you do that? By building a tall tower and dropping something from it. You can even fire the object upward and allow it to fall back down again. In this way, you can increase the period of weightlessness a bit more. And then you have a few seconds in which to conduct experiments under weightless conditions on Earth.
And that's exactly what they're doing in the Drop Tower in Bremen, conducting experiments under weightless conditions on Mother Earth.
Orbiting research labs are difficult to gain access to. It costs a huge amount of money and takes a long time. So the obvious solution was to develop a test facility where you could create weightless conditions, at least for a short time, on Earth.
The principle of the falling apple gives the scientists in the Center for Applied Aerospace Technology and Microgravitation, or ZARM for short, 4.7 seconds of weightlessness.
In the drop tower, we allow experiments in drop capsules to fall. The drop capsule is basically a complete laboratory like you'd have on the ground. During the free fall time, it's weightless. We put the capsule in the drop tower, pull it to the top, pump all the air out of the drop tube so that nothing slows its fall later, and then let this laboratory, the drop capsule, fall.
The drop distance in the tower is 110 meters, 4.7 seconds to conduct the experiments. An important field of research at the drop tower is the behavior of liquids under weightless conditions. At the bottom, the capsule plunges into a deceleration chamber filled with polystyrene balls. The drop tower in Bremen is unique in Europe. Experiments under weightless conditions are carried out here on a daily basis.
We can see the drop capsule, which in this case is almost too long to fit in the deceleration chamber. We have to split it into two sections to get it in here at all. It's now being prepared for the next experiment. During the freefall time, we're investigating the auto-ignition of two neighboring fuel droplets under weightless conditions.
Inside the capsule is a complete laboratory, including lasers, cameras, and complex measuring instruments. Finally, a tip is fitted to the bottom end of the metal cylinder. It reduces the impact impulse when the laboratory, which by then has accelerated to 168 kilometers per hour, plunges into the deceleration chamber. The prepared capsule is then pulled to the top of the drop tube by winch and anchored in place.
The capsule is hanging at the top and gets dropped. It moves very slowly at first, so it doesn't feel much air resistance, but as it gets faster, the air resistance would increase, which would slow it. We wouldn't have microgravity, no weightlessness, which is why we have to create a vacuum.
Evacuate means creating a vacuum in the drop tower. To do this, it's sealed, and 18 high-performance pumps begin to suck out the air. The process takes about 1.5 hours. Once completed, the drop tube is almost devoid of air and has just 1/10,000th the normal atmospheric pressure.
The advantage of a drop facility on Earth is the excellent quality of weightlessness, the best achievable, in fact, even better than we can get in space. We have the possibility to improve things we didn't do well today, tomorrow. In space, we'd have to wait 10 years until maybe we get another chance.
In the control room, they monitor the evacuation procedure. The entire facility and the experiments are controlled from here.
We're currently evacuating the tower, which means we're sucking all the air out. The structure is sturdily built, of course. The entire tower is made from a long steel tube that's externally reinforced with rings so that it can't implode. If I take a bag and suck, it crumples up, and so this doesn't happen with the tower. It's fitted with reinforcing rings and is engineered accordingly.
Researchers from around the world conduct up to 800 experiments a year in Bremen.
When we're ready, the experimenter decides when to launch. We specify the time window and say, ready when you are.
The scientists now take control of the experiment. The last of the cables are disconnected from the capsule.
Authorization, please.
The moment of launch. Quiet, unspectacular.
Release.
The retaining hook is disengaged. The laboratory drops. 4.7 seconds for the scientists before the laboratory lands in the deceleration chamber. The initial evaluation begins immediately afterwards. After the drop, the tube is filled with air again, and the laboratory retrieved from the deceleration chamber and freed of polystyrene balls. The big advantage of the drop tower: the morning experiment can be repeated again in the afternoon. The free fall time can be increased to 9.3 seconds. In this case, the laboratory capsule isn't dropped, but fired upward by a catapult in the foundations of the tower. The catapult launch doubles the distance the capsule travels, and thus the free fall time as well.
The moment the drop capsule leaves the catapult, that is, no propulsive forces are acting on the capsule, just gravity, the capsule coasts weightlessly upwards, slows down, changes direction, and falls back down along the same path. If you were in the capsule, you wouldn't notice it getting slower, stopping for an instant, changing direction, and falling down again. In this way, we can almost double the experiment time from 4.5 to 9.3 seconds.
Thanks to the frictionless free-fall flight, the scientists at the Center for Applied Space Technology and Microgravity can eliminate the effects of the Earth's gravity for a short time. The drop tower in Bremen allows weightlessness to be achieved on Earth, and does so several times a day. Gravity governs our lives, but anyone can escape its grasp for a short time.
You can experience true weightlessness even on Earth, but only for a brief time. Take a swing, for example. It swings up, reaches a turning point, and then swings back again. At the moment it becomes slower, the force of inertia is pointing upward and balances out the downward force of gravity. It's the same thing with a trampolinist, as we see here. From the moment he jumps up, he gets slower. The force of inertia is upward, the force of gravity downward, and he's really weightless, even if it's only for a few seconds.
As familiar as gravity seems to us in our everyday lives, it's nonetheless puzzling. Newton's law of gravitation was a milestone in physics. It not only explains motion under the influence of the Earth's gravity, but also how the stars, planets, and entire galaxies move in the universe. In 1915, Albert Einstein presented a totally new view of the universe. In his general theory of relativity, he treats gravitation not as a force, but as a property of the geometry of space and time.
In his view, gravitation was geometry, so objects don't attract one another because something somehow falls down. They're attracted because space-time has a particular geometry. That's very difficult for us to imagine because we can only think three-dimensionally. To do so, we have to think in higher dimensions, as it were. We humans can't do that. You can only do it on paper with mathematics. But it does mean that if we know how much matter there is in the universe, we can work out the geometry of the universe, of the space in space-time.
Einstein's general theory of relativity and his new way of looking at the universe led physicists to discover a string of new phenomena and models. And his genius forms the basis of our modern digital life today.
Einstein first invented special relativity, which describes the situation for bodies moving at constant velocity, that is, not experiencing acceleration. He wasn't entirely satisfied with that, so he considered what happens in other situations. And the general theory of relativity makes allowance for accelerating frames of reference too. And he discovered that you could describe gravitation using such a theory. The clocks on board GPS satellites, for example, have to be corrected for this relativistic effect. In other words, if Einstein hadn't invented it, the GPS system wouldn't work. We'd continually get lost.
But even in the 21st century, while physicists and astronomers know a lot about gravitation, science is still a long way from understanding everything. But still, Einstein's contribution was a huge step forward.
Today, we know what gravitation actually is. A force field that an object, a mass, generates around itself. And what's great is that Einstein explained what this force field is. According to him, it's the distortion or curvature of space around an object. Take my body. The warping of space right next to me is much greater than further away. And the same applies in all three spatial dimensions. Another object creates its own distortion, and both these distortions can see each other, and that's what the gravitational force is. Because it's difficult to picture, we use an analogy. Instead of three-dimensional space, we use a two-dimensional surface. The depth of this funnel indicates how strong the curvature is. So down here, space is more strongly curved than further out. And if we accept this analogy, it's immediately apparent why planets, for example, move in elliptical orbits around another massive object. Here we see a planet orbiting the Sun. The Sun is here. You can immediately see that this is an ellipse. So we understand that curved space generates elliptical orbits. To summarize, gravitation is nothing more than the experience of curved space.
Einstein's imaginative power changed our picture of the universe overnight. Modern astronomy has been heavily influenced by his theories since then. Many astrophysical processes can only be satisfactorily explained using Einsteinian gravitation. One example is the gravitational collapse of massive stars toward the end of their lives. They collapse in on themselves to form a compact object like a neutron star or a black hole.
When the center of a star collapses, that is, when the external forces become so great that the atoms and the nucleons are no longer able to push back, the outer layers get squeezed more and more tightly together. At some point, the electrons orbiting the atoms are forced into the nucleus, and you're left with a neutron star. Basically, a huge atomic nucleus that's only held together by gravity. And these neutron stars exist and possess incredible magnetic fields and emit signals we can detect. If the mass of the star and thus the gravitational force is greater still, at some point you end up with a black hole.
Einstein's theory also makes a surprising prediction. For instance, that light will be bent by gravity. Evidence of this is given by so-called gravitational lensing. As with a glass lens, light from a distant object is bent by an object located between it and the observer. But much about the force of gravity is still shrouded in mystery. We know that objects attract one another. How strongly they attract depends on their mass and how far apart they are. If one body is much heavier than the other, it attracts it more strongly too. This effect could be clearly observed when the small comet Shoemaker-Levy passed by and was captured by Jupiter. The tidal forces generated by Jupiter's mass ripped the comet apart. The debris eventually crashed into Jupiter in 1994. Large masses attract small masses. Planets capture smaller celestial objects. One reason why massive Jupiter has so many moons. Many of them did not form in its vicinity, but when they approached the giant planet too closely, they were forced into orbit by its gravity. The second giant in our planetary system, Saturn, further demonstrates the effect of gravity. Its rings are formed by innumerable objects that are gravitationally bound to it. On a large scale, gravity is the dominant force in the universe, and it will eventually be responsible for its demise.
Our everyday experience teaches us that friction is all-pervasive, including out in space. But friction means a loss of kinetic energy, and when things slow down, their inertial force, and thus centrifugal force, is lower. And so the forces that oppose gravity are constantly diminishing. In other words, over the long term, that is, many billions of years, gravity will override everything. What does this mean specifically for the end of our universe? Well, there won't be any more galaxies. All the solar systems and their planets will fall into the black holes in the center of every galaxy. And all that will be left will be isolated black holes. That's the bleak end of our universe. But we can exploit gravity for space travel too, because the gravitational fields of orbiting planets are ideal for performing flyby maneuvers.
Space travel using gravity rather than fuel. Navigating a spaceship or a probe through our planetary system is an extremely complicated business, as its trajectory is affected by every mass in the system. But it's exactly these effects that are required to travel deep into space.
If you want to send a probe, for example, into the outer solar system, you don't send it directly to Pluto or wherever. You use the fact that the probe will be attracted by Jupiter, and the energy of Jupiter can be exploited, as it were, to accelerate it.
Mission planners use the flyby of celestial bodies to accelerate, slow down, and even change the trajectory of their spacecraft. Having been accelerated in this way, the probes Voyager 1 and 2 became the first man-made objects to leave our solar system and are now venturing ever deeper into the universe beyond.
You can work it out on a computer. You don't need anything more than Newton's law of gravitation and a big computer.
The European Space Agency ESA's Jupiter mission JUICE also hinges on these principles of predictable celestial mechanics. The probe, developed by the German Aerospace Center DLR, will study Jupiter and, in particular, its moons more closely. JUICE will embark on a long journey and play an important role in the search for extraterrestrial life in our solar system. It will take the probe 7 years to reach the Jupiter system and then enter its orbit. It will fly by the moons Europa, Callisto, and Ganymede, collect data, and use the gravity from the moons to perform trajectory corrections. The probe will exploit the effects of gravity for its long journey to Jupiter. By repeatedly passing by the Earth, it will acquire the necessary momentum to ultimately reach Jupiter and enter its orbit. After 3 years in orbit around the gas giant, JUICE will then leave Jupiter and head for its final destination, Ganymede. The probe will enter into polar orbit around the Jovian moon and study it from an altitude of approximately 500 kilometers. Part of its mission will be to determine whether there's a global ocean of liquid water beneath Ganymede's ice crust, a prerequisite for potential life. The probe will then gradually orbit lower and lower until it finally crashes into Ganymede's surface.
Gravitation is just one of 4 fundamental forces of nature. There's also the strong force, the electromagnetic or electrostatic force, and the weak force. These two, the strong and weak forces, only have an effect at microscopic distances, so we can ignore them at cosmological scales. The electrostatic force has the property of being both attractive and repulsive, which means that when I have a large quantity of material, these forces average out to 0. Gravitation is very different in this respect. Masses always attract, and if I have large amounts of mass, the gravitational force is correspondingly large. My small mass can't generate much gravity, but the Earth underneath me generates a really powerful gravitational force. This is why on small scales the electrostatic and gravitational forces are weak. But the opposite is true on cosmological scales where gravity is the dominant force. We saw earlier that space has a fabric, and that masses can warp this fabric. But distortions can vibrate too, so there ought to be waves. And there are. And because distortion means gravitation, there would have to be gravitational waves too. And this opens up a whole new field of research, namely gravitational wave research.
On September 14, 2015, 2 detectors in the USA simultaneously recorded a very special signal. The first ever proof of gravitational waves. It opened up a whole new window on the universe for science. It was proof that the fabric of space-time is not static, but can change. The gravitational waves traveled 1.3 billion light-years to reach Earth. They are ripples in the fabric of space caused by a cosmic cataclysm.
On September 14, 2015, they just completed a phase in which the sensitivity of the detectors had been increased. Strictly speaking, they were the last of the scientists to work on the device. They switched it into science mode, so it worked with very low noise. They left for home just 3/4 of an hour beforehand, when the detectors picked up a signal, a textbook signal.
Two black holes, one 29, the other 36 solar masses in size, smashed into each other. The collision of these two gravitational giants was the origin of the recorded signal.
The initial reaction was a bit skeptical, however, due to the fact that we've been working on this for so long. We'd always looked forward to this day with excitement and dedicated a large part of our lives to improving the detectors in order to finally detect gravitational waves for the first time. And when it finally happens, and looks just like in the simulations and presentations you've seen and given yourself, then a part of your reaction is disbelief. Is this real?
Stimmt das denn jetzt wirklich?
And once again, Einstein was right. In 1915, he gave a presentation in the Prussian Academy of Sciences where he also talked about the existence of gravitational waves.
Gravitational waves were the last of the predictions made by Einstein's general theory of relativity that was yet to be confirmed. Many other things had been proven with great precision over the years, but gravitational waves were still elusive. The fact that we've now managed to detect gravitational waves is further confirmation of how good Einstein's theory of general relativity is.
The waves were measured by the LIGO detector in the USA. The idea for gravitational wave detectors like LIGO had been described as far back as the 1960s. They measure the change in length of two laser paths. In the LIGO detector, the laser beams pass through two 4-kilometer-long vacuum tubes that are positioned at an angle of 90 degrees to one another. Mirrors at the end reflect the laser beam back to its point of origin.
The
principle used to detect gravitational waves is relatively simple from a physics perspective. You have two long arms. You fire light into this arm, and if the length of this arm changes, the interference pattern changes. This interference pattern is very sensitive to changes in length. We're talking about absolutely minute length changes, though, just tiny fractions of the diameter of an atom. And that's what makes it difficult. You naturally have to eliminate all spurious signals. That was the biggest achievement, really.
The LIGO detector was built in the mid-1990s, but the breakthrough was only made once it was upgraded. The technology for this was supplied by GEO 600, a gravitational wave detector at the Max Planck Institute for Gravitational Physics in Hanover. GEO 600 is designed along the same lines as LIGO, just much smaller.
Our goal with this GEO 600 detector was to achieve a sensitivity similar to the other detectors. GEO 600 has an arm length of 600 meters, whereas the LIGO detectors have an arm length of 4 kilometers. So in order to achieve the same sensitivity to gravitational waves, it had to be more sensitive. This couldn't be achieved with the technology used by LIGO, though. As a result of this constraint, more advanced technology was tested and developed for the GEO 600 detector. A significant portion of the GEO 600 technologies that were developed here were then incorporated into the second-generation advanced LIGOs.
Proof of gravitational waves resulted in the Nobel Prize for 3 U.S. physicists in 2017. They represent the thousands of scientists who worked on the project and contributed to its success.
In
the field of gravitational wave research, we're still in what's actually a good situation where there's healthy competition. Of course, everyone wants to be the best and the first, especially when it comes to such a complex and difficult undertaking. On the other hand, no one can do it on their own.
The first direct proof of gravitational waves was a milestone in the study of the universe. Until then, scientists were reliant on electromagnetic waves, such as light or X-rays, for their observations. With the gravitational wave observatories, they now have a completely new tool at their disposal.
For Einstein, it was as clear as day. There's a fabric to space. Fabric can ripple. And soon after publishing his general theory of relativity, he predicted that gravitational waves must exist. But these ripples are so tiny. They're on the scale of the diameter of an atom, which is why you need absolute calm to measure these ripples. And where can you find that? Up in space, of course. Which is why the future of gravitational wave research is in space. And that's why the European Space Agency, ESA, is planning a new project named LISA to measure such waves from up there.
There are no disturbances in space like the vibrations or thermal problems you get on Earth. This should dramatically increase the accuracy of the measurements. As a test for the European Space Observatory for Gravitational Waves, ESA's LISA Pathfinder mission launched into space in December 2015. Its objective, to evaluate technologies and detection methods. LISA Pathfinder was positioned 1.5 million kilometers from Earth at the L1 Lagrange point. L1 is a point of equilibrium between the Earth and the Sun. Here, a probe remains virtually at rest. The probe's payload is the LISA Technology Package, LTP. It consists of two free-floating test masses. Between them is a laser interferometer, which precisely measures the position, orientation, and acceleration of the two test masses. The probe surrounding them is constructed to precisely track these test masses and thus eliminate all disturbances. This ensures that the test masses are absolutely weightless. LISA Pathfinder was a major success. The disturbance suppression it achieved exceeded the stipulated requirements by a factor of 5. The actual LISA mission is planned for 2034, a gravitational wave observatory stationed in space. A configuration of 3 identically constructed probes is planned, similar to the LISA Pathfinder. The 3 probes will fly in a triangular formation at vast distances from one another. On board the master probe is a laser, whose light gets reflected by the other 2 probes. Since, like LISA Pathfinder, all 3 probes travel absolutely free of external disturbances, they can study gravitational waves by precisely measuring the distance between them. The 3 probes form an enormous triangle of light in space between the Sun and the Earth.
The 2 LIGO detectors have an arm length of 4 kilometers, and the Virgo detector has a 3-kilometer arm length. We don't have these limitations in space. In the case of LISA, the probes will form an equilateral triangle with a side length of 2.5 million kilometers, so many magnitudes larger. And this allows it to detect much, much lower frequencies as well.
It's hard to imagine the scale of LISA. A laser beam will take 8.5 seconds to cover the 2.5 million kilometers between 2 probes. The 2 reflected laser beams will then return to the master probe.
Every time you sit there and think, wow, If this is possible, why are there so many other things we can't get right? Why are there still dead zones in the cell phone network when they can pull something like this off? It's mind-blowing.
Gravitational wave research from space is an important step toward better understanding the universe. Scientists hope the LISA Observatory will detect many other events in the universe in order to better understand and classify them. Researchers are already working on new types of gravitational wave detectors on Earth, too.
The plan is to construct new infrastructure for the so-called third generation of detectors. It will all be built about 200 meters beneath the Earth in order to eliminate the disturbances on the surface. And thanks to the increased sensitivity of the third generation gravitational wave detectors, we should be able to see a whole range of other events and advance other areas of scientific research.
Andere Ereignisse sehen können, andere Wissenschaft treiben können.
The European Einstein telescope concept describes an enormous detector buried underground. A third-generation gravitational wave observatory with 10-kilometer-long arms arranged in a triangle. The scientists expect 10 times greater sensitivity thanks to the noise suppression effect of being underground. The enormous underground laboratory is to be installed approximately 200 to 300 meters beneath the Earth's surface. Its exact location has yet to be decided, however. First, the ET Pathfinder will be built in preparation for the project, a scaled-down prototype of the Einstein telescope. The mini detector is being developed at the University of Maastricht and will have an arm length of just 20 meters. This isn't sufficient to detect gravitational waves, but that isn't the objective at this stage. The test facility in Maastricht will develop and test different technologies for then equipping the final observatory. The Einstein telescope should be able to detect gravitational waves from much more distant events than has been possible until now, and thus provide new insights into the evolutionary history of the universe. Gravitational wave astronomy is coming of age.
Gravitational wave research was somewhat of a niche pursuit before they were detected and verified. But now it's becoming mainstream.
The astronomers hope that gravitational wave research will allow them to look back into the past as far as the Big Bang.
That would be amazing. If 14 billion years after the Big Bang, we could still detect the gravitational waves emitted back then. Another example of something that would be amazing to detect: every gravitational wave can be interpreted as a particle, the same way light waves can be interpreted as photons. And photons can be deflected, for instance, by mirrors. Similarly, gravitons ought to be deflected by singularities, like black holes, and we should be able to detect this too. Regardless, the main point is that the more sensitive these gravitational wave detectors become, the further into the universe we'll be able to look, and the more we'll learn in the future. In this respect, we have a completely new cosmic detector.
Gravity. It determines the geometry of space and time. While it may be the weakest of the four fundamental forces of nature at small scales, on cosmic distances, it dominates the universe. It's a mysterious force that governs everything, from the Big Bang, the beginning of space and time, to our own existence. Understanding it completely is the key to our universe.